Okay, hello everyone. Welcome back to the Intercontinental Seminar Series on Gravity and Cosmology. So today we are very happy to have Professor Atsushi Nishizawa-san to give us a presentation. Professor Nishizawa-san, he got his PhD from Kyoto University in 2009, and right now he is a professor in Hiroshima University. And he is an expert in testing gravitational theories and also the gravitational wave physics. So today he's going to talk about nonlinear tests of gravity with gravitational waves. And so during the talk, if you want to ask any questions, you just feel free to raise your hands and we will make you ask questions. So stage is yours, please. Yeah, Professor Nishizawa-san.
Thank you for the introduction and organizers for the invitation to this nice seminar series. And everyone for joining. So I'm talking about nonlinear test of gravity with gravitational waves. So so this is the outline of my talk. So first, I will introduce the test of gravity in general, then focus on what is new with the gravitational wave observations. Then I move on to the test done so far, and focusing on waveform consistency test. This is mainly done by LIGO-PIRGO-Kagura collaboration. Then I will talk about the parameterized waveform for major phase. So this is a work, so we have done recently. And then, another interesting phenomena of nonlinear gravity is gravitational wave memory effect. And then I will summarize my talk. Okay, so first, why do we test gravity? So general relativity has been tested at the precision of 10 to minus 5 in the weak gravity regime, like in solar system or binary pulsar. And so this is very good, and general relativity is almost okay. And also, gravitational wave emission is tested with binary pulsars at a precision of 4.1% level. So this is also very good. But we don't know about gravity in that cosmic accelerating expansion or dark matter may be explained by gravity. Also, the quantum effect of gravity is unknown because we don't have quantum gravity theory. Also, in general relativity, there is a singularity in at the time of Big Bang or at the center of a black hole. So the we may need to explain non-singular non-singularity of these cases in quantum gravity theory. So so the question is in what environment the new aspect of gravity appears. So this slide shows a summary of tests of gravity so far. So the horizontal axis is a potential, so gravity strength, weak to strong regime. And the vertical axis is a scale. So at the top, very large scale, and at the bottom, very small scale. And the solar system test is located here by Mercury and gravity probe B and Moon. And the binary pulsar is, gravity strength is slightly stronger and is here. And also another one is here. So this regime is a quasi-static and weak regime of gravity. and very well tested. And another regime of gravity is here. So there are observation of event horizon telescopes. And so this is also quasi-static regime, but gravity is stronger. And yeah, it's very close to the horizon of black hole. And this region, there are also binary neutron star mergers or binary black hole mergers. And so this regime is strong and dynamical. So this can be tested by gravitational wave generation. And another interesting regime is here. So there are galaxy clusters, or something in the Milky Way. So this is at the cosmological scale, and due to the cosmic expansion, so this regime is dynamical one, and so this regime can be tested by gravitational wave propagation or other cosmological observations. So in this talk, so I'd like to focus on this dynamical and strong regime of gravity. And so in the end, so we need to test the nonlinear nature of gravity. So here, so I'd like to introduce one example of modification of gravity at a nonlinear regime of gravity. So one of the theories is Einstein-Dilaton Gauss-Bonnet gravity. And in this theory, one scalar field exists, and which couples with the Gauss-Bonnet term. So this Gauss-Bonnet term is a second order in curvature. So this term becomes important in the strong regime of gravity or nonlinear regime of gravity. So in this simulation, the gravitational wave is computed by numerical simulation. And so the scalar field is treated as a perturbation to the spacetime. So this general function of theta is expanded in terms of theta, and in this simulation, linear term is taken. So as you can see, the amplitude of gravitational wave is very enhanced around the merger. And this doesn't appear in the early stage of inspiral, but as gravity becomes stronger, then the amplification becomes larger and larger, and at the time of merger. So this nonlinear effect enhances the amplitude very much, depending on the coupling strength. And so this simulation is a perturbative treatment, but recently there is another full numerical simulation, and so in their result, the amplification doesn't occur efficiently. So their results are discrepant. But what I'd like to emphasize here is that so around the merger, the nonlinear effect can be important, and the amplitude of gravitational wave can deviate very much from GR prediction. And also in the simulation, scalar gravitational waves are computed. So these scalar emission is come from the the dynamics of scalar field. And so the top one is a scalar monopole mode. So this is a almost constant during the inspiral and merger, but after the merger, the amplitude jump to the another constant value. And so this is a scalar memory effect, and I will come back to this phenomena later. And the second one is a scalar dipole radiation, as usual. And also, so in this simulation, scalar quadrupole is emitted. And as you can see, the amplitude of quadrupole radiation is not suppressed. And yeah, similar to the dipole amplitude. So all of these scalar Gaussian waves need to be considered when we test gravity with binary black hole or binary neutron stars. And the observation, so there are many events detected so far. And so 9 events have been detected until O3. And now, so O4 observation is running, and first half of O4 observation, so there are 84 event candidates. So yeah, which is during the first 9 months of the O4 observation. So the number of Gaussian wave events is increasing rapidly, and we have seen, from small mass black hole to massive black hole. Also, the neutron star black hole binary or binary neutron stars. So when we test gravity, so we will use some of these events depending on the characteristics of test. So we will choose better event from these many events. Then, yeah, so next I will talk about the waveform consistency test. So Gaussian waveform is, during inspiral phase can be derived analytically. So by post-Newtonian expansion, so B's velocity is given by this combination. So so this is small parameter, so we can expand with this as a series of velocity. So the phase part is written like this. So there are many terms, but what is important is here. So yeah, so recently, so the post-Newtonian expansion up to 3.5 orders is known. So so each term has different dependence on frequency. So each term can be tested by comparing with GR prediction. And in the test, so we usually do this kind of analysis. So the each post-Newtonian coefficient is shifted slightly from the GR prediction. Then you have phase shift here, and it is written like this. So this is the additional phase shift from GR phase shift. And when GR is correct, so all these delta phi I are 0, then the phase shift is 0, and the GR prediction recovered. And so in general, so we need to consider all deviation at each post-Newtonian order. But in data analysis, it is quite difficult and computationally very expensive. So, what is done in the actual test is changing one of the coefficient. Then test whether it is consistent with 0 or not. So this is a result of the post-Newtonian test. And here is Newtonian order. And so this order is tested very well. And deviation from GR is allowed up to about 10%. As this is 0.5 PN order, and there is no coefficient in GR at the 0.5 PN order. So this is the absolute deviation. And yeah, so deviation is allowed deviation is larger, up to 30%. And this is 1 PN order, 1.5 PN order, and they are constrained also. Yeah, so relatively good. But at the higher post-Newtonian order, so the vertical axis is different. So this is here is 100% deviation, and almost all coefficients are not constrained well. And dipole radiation is yeah, very well tested, and it is a 0.1% level. So the conclusion from this result is that so higher than 2 PN order is not constrained yet. So still 100 deviation from GR is allowed. Then so there is another test done by LIGO-Virgo Kagura collaboration. And so idea is like this. So first, waveform is separated into two parts, inspiral part and post-inspiral part. And so each part is analyzed separately. Then the yeah, from the inspiral part, so we can measure the mass of binary and also spin of binary. So we know, so we can estimate M1, M2, Chi1, Chi2, so these are spins. Then from these parameters, so we can estimate the final mass of binary. So for binary black hole, so there is a fitting formula from numerical relativity simulation. So once initial parameters are given, then the final mass and the final spin of black hole is computed. So we can estimate MF and AF from inspiral phase. On the other hand, so we can directly estimate black hole mass and spin from merger-ringdown phase. Then we can compare these two masses and these two spins. So this is a result. From the inspiral phase, spin and mass distributed yeah, so within this contour. And from post-inspiral part, so we can constrain in this region. So here is the overlap. So overlap means in-spiral phase and post-in-spiral phase are consistent. So, so this is the first gravitational wave event, and so the consistency is well tested. And yeah, so it was consistent with GR. So if there is no overlap region, then GR is excluded. And yeah, so far, so we have detected many gravitational wave events. So we can use them to constrain. Then, so each contour corresponds to each event, and so combining these events, so so this shaded region is a final constraint. So the deviation mass and spin from GR value is very small. So 10% deviation is allowed, but yeah, very constrained. But if you look at carefully, so some event is deviated from zero value. So so the yeah, so LIGO-Virgo collaboration tested this bias very carefully by injecting gravitational waveform to the noise, and how they are biased. And so finally, so we found that the bias is caused by noise. But this kind of bias often occurs in actual data analysis. And another interesting
Sorry, Nishizawa, I have a question in the previous slide. So, do you mean that if you have more and more events, then you can shrink the gray region more and more? Is that right?
yes.
So right now here there are only 5 or
Yeah, so they selected better events for this test, and so here, yeah, maybe several events are selected and plotted,
ah
and yeah, so yeah, most of them are consistent with zero, but some event deviated from zero, and yeah, so you can see this peak is slightly deviate from zero, but still it is statistically consistent with zero.
mm-hmm.
But if there exists actual deviation from GR, so by combining more events, so that this deviation becomes larger, and finally it yeah, move to the outside of the statistical range, statistical error.
I see. Okay, thank you.
So there's another test, residual test. So, so in this test, best fit GR waveform is subtracted from data, and then the residual signal is evaluated. So this residual signal, so when they compute SNR for this residual signal, a coherent signal is considered. Sorry, coherence between detectors is considered. So this horizontal axis is a SNR of original signal. And after the subtraction, so the residual SNR is this vertical axis. So, so this event has a residual SNR equal 10. So, yeah, um, yeah, so relatively so larger residual remain after the subtraction, but the p-value evaluated is not so small, meaning that noise is noise is likely to produce this kind of residual. And uh, so the smallest p-value is this one. So in this case, the original SNR is about 14, and the residual SNR is 8. And but the p-value is 0.05. So this is not so significant. So yeah, so we are considering so this one is caused by noise. Okay, so this is a summary of such method. So yeah, GR consistency test, yeah, mainly done by LBK collaboration is this kind of test. So so in this test, so they investigate the consistency of signal with GR. But so the advantage of this test is a general test, and they use the GR waveform, but they don't assume any specific theory of modified gravity, but low sensitivity. And also, when deviation from GR is found, it is difficult to specify type of deviation and difficult to interpret it. So while waveform-based test is waveform is assumed in specific theory of modified gravity, and so this test is model dependent, of course, but sensitivity is higher, and deviation from GR is parameterized. So it is easy to interpret the deviation. So it is the advantage of waveform-based test. So yeah, so in this talk, so I will focus on waveform-based test. So it is a parameterized waveform for major phase. So the in the previous test, so the waveform is divided into two parts, inspiral part and post-inspiral part. But most interesting regime of gravity is nonlinear regime. So, so we want to test the waveform around the merger. So, and also, so we know the post-Newtonian waveform for the inspiral part, and also ring-down waveform for yeah, from black hole perturbation. So in this linear regime, linear perturbative regime, so we know analytical waveform, but we don't know the waveform around the merger in yeah, general theory, sorry, so alternative theory of gravity. So yeah, so in general, so this nonlinear regime is solved by numerical simulation, and the waveform is computed by the simulations. But there exists a phenomenological waveform. So this is a fitting waveform to numerical waveform. So yeah, so by given many coefficient parameters, then the waveform is computed analytically. So so our idea for waveform parameterization is as follows. So we use phenomenon D waveform. So this is a non-spin precessing quadrupole minor black hole waveform fitted to numerical simulation in GR. And for this waveform, so we treat beyond GR effect perturbatively. And also we assume that the inspiral and ring-down paths are same as GR waveform because so in this regime, gravity is weaker and non-linearity would be weak. And then we introduce a new parameter to the merger part for the as a leading principal component of original coefficient of the phenomenon D waveform. So as I mentioned, so phenomenon D waveform has many artificial parameters. So we try to diagonalize them and pick up a few important parameters. Also, we need to consider radiation reaction, so which is energy and angular momentum losses, because so we assumed ring-down part is described by GR prediction. But if merger phase is modified, then final mass and spins are modified. So ring-down part is no longer consistent with GR. So we need to change the final mass and the spin depending on the energy and the angular momentum emission during the merger phase. So by considering this effect, so waveform is physically consistent through the merger from the inspiral to merger and ring-down phase. So this is a waveform we constructed. And after some investigation, so we introduce only one parameter to amplitude. So the parameter controls the amplitude around the merger. And the ring-down part is not the original GR1 because so we consider the energy and angular momentum loss in the merger part. So they are also modified depending on this gamma 1 parameter. So this is a phase modification, and we also introduce only one parameter to.
Nishizawa-san,
Yes.
Alexandra has a question.
Hi, I have a question.
Yeah.
When you say that the ring down part is different, do you mean that the quasi-normal modes are other quasi-normal modes, let's say with different frequencies, or are you talking in the regime before the quasi-normal mode starts?
Both. So first, so this modification parameter changes the amplitude at the merger, the peak amplitude. So this affects the ring down slightly it affects the ring down frequency, but we also consider the energy and angular momentum loss. So the two effects affect the ring down frequency and damping time. So so this is a combination of them.
Okay, thank you.
Yeah, so I didn't say, so we connect each part smoothly. So modification here affect the later part by the connection, smooth connection. So this is phase modification, and so one parameter controls this kind of phase shift. Usually, the phase has two parameters, coalescence time and coalescence phase. But what we found is that the combination of these parameter is fine. So yeah. So after analyzing the principal components, so we pick up one parameter to control the phase like this. So the waveform is constructed like that, and then what is important is the application to the specific theory of gravity. So we checked if a waveform is correctly fit to the modified waveform in a specific theory. So in Einstein-Dilaton-Gas-Von gravity, the waveform is public. So so Okunkova provide open code to compute this waveform, and changing the coupling strength of scalar field to Gauss-Bonnet term, the amplitude changes like this. And the phase is also slightly shifted. And so this is a result of fitting. So black dashed curve is GR waveform, and this green one is a numerical waveform of Einstein-Dilaton-Gas-Von gravity. And our fitting waveform is a blue one. So they are almost overlapped. And you can see slight deviation from GR, but so green one and blue one are almost overlapped. So this is a stronger coupling case, and deviation from GR is larger, and but still we can fit the numerical waveform very well. Actually, so here is a slight deviation, but this is not a problem because this mismatch is smaller than the statistical error of O4 and O5 observations. So we can use this waveform for the next several years. And stronger coupling, more stronger coupling case. And in this case, fitting is not so good. So the mismatch is smaller than the statistical error of O4, but marginal for O5. And also this coupling strength is the edge of perturbative treatment. So the perturbative formalism is start to break down. So this is a range, valid range of our waveform. Okay, then so there are many things we should do next. So the waveform is constructed, and next, so we need to constrain these two parameters with the observational data. And also, so we have not considered the multipoles higher than quadrupole and spin precession. And so, we plan to apply to the state-of-the-art inspiral-merger-ringdown waveform. Yeah, so yeah, in principle, our method can be applied to more complicated waveforms. And so we have not considered the radiation reaction through the existence of additional scalar vector fields and polarization. So if we consider these additional degrees of freedom for the energy and angular momentum loss, then we may need to introduce another parameters. And yeah, also, yeah, we need to study data analysis with this waveform. Okay, then yeah, so finally, so I'm talking about Gaussian wave memory effect. So Gaussian memory effect is a persistent change of space-time due to energy loss from a system. So this is a Gaussian wave amplitude change, and so this is given by the energy loss from the system uh, at the final time and initial time. And MA is a mass of system A. VA is velocity of center of mass of system A. So yeah, so this equation means is a integral of energy injection is uh, yeah, so energy injection is integrated over all angles, and then so the amount is compared uh, between the final time and the initial time. So as the energy injection is larger, the jump of Gaussian wave amplitude is larger. And so in this case, energy injection is whatever fine, like neutrino or actual mass injection or yeah, whatever. But the interesting case is Gaussian wave nonlinear memory. So first, so this memory effect is um, found by Christodoulou. So in this case, energy injection is by Gaussian wave itself. So energy injection of Gaussian wave produces the persist change of Gaussian wave amplitude. So in this, yeah, in this sense, so this is nonlinear effect. So this is this shows a waveform of uh, Gaussian wave from compact binary. So this is sharp signal, and yeah, this is a merger time. And so this is a Gaussian wave memory effect. So the energy energy emitted is accumulated during the inspiral phase, but still it increases slowly. But around the merger, the energy is injected uh, uh, yeah, yeah, loudly. So the Gaussian wave amplitude jumps here. So after the merger, Gaussian wave amplitude becomes constant. So yeah, so the this constant Gaussian wave amplitudes cannot be detected by detectors, but this kind of jump can be detected because this is a time-dependent. Uh, uh, yeah, the time-dependent deformation of space-time. So, so this effect has been searched from the observational data. And so the first, the amplitude of memory effect is assumed like this. So if A equal 1, so it is a GR prediction. But in other case, A is different from 1. So anyway, so it is important to test the value of A. So from 88 events from GWTC 3 catalog, so they found this constraint. Blue one is a constraint from 88 event. And at 95% level, A is less than 23. But so yeah, among these events, so 3 events are very noisy. So they removed these 3 events. Then the constraint got stronger, and they found A is less than 15. Anyway, still the constraint is weak. But in the future, this effect can be detected. So when we detect from 1,000 to 2,000 binary black hole, we can detect this event. So this shows the accumulated SNR. So yeah, from for observation, so the SNR increases like this. Then yeah, sensitivity becomes better. Then SNR increases rapidly like this. And after 2 years observation, it exceeds 3, and we can detect something. And so I'd like to introduce another interesting case, scalar glacial wave memory. So yeah, at the beginning of this talk, so I introduced the scalar glacial wave memory in numerical simulation in Einstein dilaton gas bond gravity. And yeah, but this memory effect can exist in more general theory with scalar degrees of freedom. So the idea is like this. So first, so suppose that there exists a massive star at the beginning, and it has a scalar field phi h. Then this massive star collapses to black hole, and scalar field changes to phi naught. And in most theory of gravity, black hole has no hair theorem, so phi naught is usually 0. But the scalar field changes from phi h to 0. So we can see the jump of scalar field amplitude, and it propagates. So it is a scalar glacial wave memory effect. Okay, so this shows depending on the parameter in the theory, so beta naught equal -3 is the strongest case, and so the scalar amplitude is like this, and so we can expect larger amplitude of scalar glacial wave memory. So we have computed the detectability of this memory effect. And so this shows the constraint on beta naught and alpha naught in scalar tensor theory. And observation of binary pulsar have already given this constraint, blue one and orange one, and from if the supernova occurs in the nearby universe, then and Gaussian wave observation gives this red constraint. So the above this line is excluded, and from the third generation detector, we can constrain more. And recently, so Kazuya Koyama-san predicted interesting case. So yeah, so in Brans-Dicke theory, without screening, then scalar Gaussian wave becomes very large, and it's contradict with observational constraint. So we cannot expect the significant SNR for scalar Gaussian wave. But with screening effect, still very large amplitude of scalar Gaussian waves allowed. And if a supernova occurs in the nearby universe, so we will see scalar Gaussian wave memory effect and constrain gravity theory very well. And yeah, so there's one caveat. So in scalar, Einstein scalar Gauss-Bonnet theory, black hole can have a scalar here, and neutron star doesn't have it. So, yeah, but still, scalar Gaussian wave memory can exist, and yeah, it would be another interesting case. Okay, so it's almost time. So yeah, I will summarize my talk. So many tests on Gaussian wave properties have given observational constraint in new regime of gravity, particularly in the strong regime of gravity. So I introduced 3 tests. So one is a consistency test. The low post-Newtonian orders are better constraint, but high post-Newtonian orders are still weakly and allowed large deviation from GR. And then I propose parameterized test of the merger part. The parameterized waveform has been constructed, and so we will constrain the model parameter with observational data soon. And the third one is the Gaussian wave memory effect. So this is also the nonlinear effect of Gaussian wave emission. And even in GR, this effect exists. And yeah, in scalar tensor theory, scalar Gaussian wave memory effect exists. And yeah, if the supernova occurs in the nearby universe, we will obtain strong constraint and test the nonlinear nature of gravity in the future. Okay, so that's all. Thank you.
Thank you very much, Nishizawa-san. Is there any question? Maybe I can ask one first. So I have one question in the parameterized test. So you introduced 2 parameters to parameterize non-GR effects, right?
Yes.
And so can you give a kind of interpretation for these 2 parameters? Because usually in the parameterization approach, you can introduce whatever parameters, but it's very difficult or not clear how to interpret physically these parameters. So I'm interested in this.
Yes. So the easier one is gamma 1. So this parameter controls the amplitude at the merger time. So yeah, so you can see. So this the amplification is, or suppression is controlled by gamma 1. Then another parameter, PCA, is controls the phase shift. But for this parameter, it is difficult to interpret the yes. So I don't have the clear answer, but it is a kind of combination of coalescence time and the phase shift at that time. So so we have investigated the so the degrees of freedom in the phase shift, and picked up a few principal component. But so other principal component are not so large and almost ignored. Then finally we picked up only this one principal component. So it is this one.
I see. So because it's very interesting to see that with these only two parameters, you can fit the numerical waveforms of Einstein, Dalton Gauss and gravity quite well, at least in the small coupling case. So like if you have other theories, as you say, with additional degree of freedom, I guess you have already an idea which new parameter that you may have to include next, right? I guess.
Yes. So so we want to check other theories, but difficulty is that numerical simulation. So there is no numerical waveform for other gravity theories. And
Right.
it is very difficult. Yeah. So maybe Chern-Simon gravity is the next candidate for checking.
I see. Thank you. Any other questions?
Sorry, I have one naive question about your final section about the gravitational wave memory effect. So I assume that in your mind, your target detector would be LIGO. So my question is, how do you isolate the DC effect of gravitational memory effect from the traditional one in that case for the LIGO detector? I mean, sorry, not Lisa. Sorry, for LIGO it's difficult to isolate because we have active correction. Now, for Lisa, is it more doable, or do we need a special pipeline to deal with these specific effects?
So that's a excellent question, and it is so the answer is it is detectable with LIGO, but also with Lisa. And so we can detect this jump of amplitude. So this is almost a step function. So the Fourier transform of step function is inverse of frequency spectrum. So it is a characteristic spectrum, and so this transition time gives a high frequency cutoff of inverse of frequency spectrum. And so you may concern about seismic noise or other disturbance of detector. And with a single detector, it would be difficult to detect this effect. because it confused with other noises. But this is gravitational wave, and we can detect this coherently among detectors. So if there are 3 or 4 detectors, then all the detectors can detect this kind of signal, and so we can confirm, gravitational wave memory, came.
So if I understand correctly, so you need first you need a coincidence test that you'd have a specific fitting of this source, and then given the source, you construct the potential gravitational wave memory effect cutoff, and then you apply it to multiple detectors to see if there are simultaneous fit.
Yes, that's right.
I see. Thank you very much.
Any other questions? If no, then maybe we can stop here. Thank you very much, Nishizawa-san.
Thank you very much.
We stop recording.